vector. Maybe to remind ourselves, what is the ratio theorem, or somebody to briefly describe what ratio theorem is.
Yes.
I believe we've all done vectors too. Is there a class that is yet to cover vectors too?
No.
Okay, then this is revision. So I expect that at least some of you should be knowing what ratio theorem is. So somebody to tell us what ratio theorem is, brief. Okay, I have not seen any hand being raised. So can I maybe quickly mention it?
Yes, please.
Kindly do.
Kindly,
Okay,
kindly.
just a minute. Yes. Okay, I seem to have lost some network there. I hope I am audible now.
Yes, you are.
Yes, we can hear you. Yeah.
Okay, when we talk of ratio theorem, this is a theorem that tells us how we are supposed to divide lines, and more so how to divide vectors. In form 2, we did position vector, and we also did midpoint of a vector. We did position vector as well as the point of a vector. So that concept is a concept that you are going to highly make use of. I hope you can see my screen from your end. Can you see my screen from your end? And if you are not responding to questions, kindly stay on mute. You only unmute when you are responding to a question. So we stay on mute unless when responding to a question. Okay, on the screen, maybe we have a Cartesian plane, the y-axis, the x-axis. Then we could have some vector, maybe call it AB. In form 2, we were told that if we wanted to get the midpoint of AB, call it maybe point M. We would normally say it is a half of A, then we add a half of B. A half of A plus a half of B. I hope you remember that from form 2.
Yes.
Yeah, this is because of some procedure that we did again in form 2, where we said that for you to move from O to M, that is the vector O to M, you needed to have maybe moved from, first of all, we have the position vector OA. Position vector OA. Remember, position vector is called position vector because this is the vector from the origin to a given coordinate. So if you have point A, then you have from O being the origin of the Cartesian plane towards A, you will talk of the position vector OA. Then we also talk of position vector OB and look at the arrow. Hii tulifanya form 2. Position vector OB from O to point B. Position because it's with respect to the center of the Cartesian plane. Now, if we have AB, the vector AB, then we are told to look for its midpoint. That is the center. Call it M. Or we can say maybe M divides AB in the ratio 1:1. M divides AB in the ratio 1:1. So for you to get the coordinates of M, in form 2 we said we need to move from O to M. The one that I have put it in dotted there. For you to get the position, or rather the coordinates of M, we need the position vector OM. Because like I have said, position vector gives the coordinate, or it can lead you to get a coordinate for a point. So ukitaka coordinate ya M, you need the position vector OM. Now from this diagram, assuming that you are told that OA is A and OB is B. So OA, from O to A, we have the vector denoted there as small a. Then O to B, we have the vector denoted as small b. Now somebody to help us to move from O to M, but you use a route that has A and B. How do we move from O to M, but using a route that has been given some letter A or letter B? Are we hearing what I'm saying?
Yes.
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 Does it mean that we've completely forgotten again vectors 1?
No.
No.
No,
Do
we
we have issues with vectors 1?
No, we are still calculating.
We have?
No.
Okay. So. Collins Kefadi, your hand is up.
Yes. So to get OM, it would be OA plus a half OB.
OA plus a half OB.
Yes.
Just a minute, I reconnect my screen. OA plus a half OB. Okay. You said OA plus a half OB.
Yes.
Okay. Anybody else with a different route?
Correct.
OA plus a half OB. We all agree with that? Melvin Manyange.
Yes. To find OM, you can use OA plus a half AB. Yeah. OM
You
is
say a half what?
AB.
Hello.
Yes. Hello.
Hello.
Okay.
Yeah.
You are lost for a second.
Somebody is saying I have AB plus OA, or you can say OA plus I have AB. Somebody else was saying OA plus I have OB. So how many agree with the first route? I mean OA plus I have AB. Or how many agree with the second route? Bramwell.
I agree with the root OA plus a half AB.
Okay. So just a minute. My network seems to be bothering me, but let me change the service provider. A minute. I'm hoping this one is more stable. Can you hear me?
Yes.
Yes.
Yes, we can hear you.
Okay. But now I'm hearing something. Just a minute. Okay. Now, for you to move from maybe O to M, like a majority of us have observed, we need to move from O to A, then A to M. O to A, then A to M. And that's why we are saying half of AB. O to A, then A to M. Are we all in agreement?
Yeah.
Yes.
Yes.
Yeah, we needed to move from O to A, then A to M. And A to M is a fraction of AB. And the fraction we've noted is a half. A half because the ratio there is 1:1. If it's 1:1, then that means AM divides AB into 2 halves. The ratio is 1:1, so M divides AB in 2 halves. That is a half or 1/2 of AB. So O to A, then A to M. Now, the reason I brought this was at least to remind ourselves that we had introduced ratio theorem, but not so significantly in vectors 1. Eventually, if you are to move along those vectors that we've mentioned, you will end up with taking a half of the first vector plus a half of the second vector, so that when you add these two, you get the vector OM. And remember, the vector OM will be the position vector for point M. And therefore, you can get coordinates of M. I hope you remember that from Form 2.
Yes.
Yes.
Yeah.
Okay, now the ratio theorem is developed from something like this. Only that this one is happening to be 1 by 1. So we might think that is always a half or a third, or this is you should not generalize from this, but you have to have remembered something at least from Form 2 before we introduce ratio theorem. Okay, now assuming that now the ratio that we are dividing the line is no longer 1:1. We say, for example, we have some line there we are told that this is the first point, this is the second point, this is A, this is, call this point T, then call this point B. Then we take a general ratio, call it M, call this N. I will rush through because I know you are told this in class, maybe you just forgot. Now, OA, remember, is some position vector. OA will be some position vector of
You can
point.
see position. No?
Then OB will be position vector for B. O being the origin of the Cartesian plane. So OA gives you position vector of capital A as a coordinate, while OB will be the position vector of capital B being the coordinate of the point B. Hiyo yote ni kazi ya form 2. Then OT will be some position vector again of capital T, and we can use capital T as a coordinate. So the coordinate we will generate from generating the vector OT will be the coordinate for point T. Hivyo iko sawa?
Yes.
Yes.
So two things. One, you should know what position vector is. A position vector is the position of some coordinate with respect to the origin of the Cartesian plane. And that position vector, when rearranged, it will give you the coordinates of that point. For example, if A was maybe having a coordinate 2, 2, I'm just using an example. If A was 2, 2, the position vector OA will be given as 2, 2 as a column vector. We take X followed by Y as a column vector. We can as well call it small a, 2, 2 again as a column vector, or we can say 2I plus 2J. The I and the J stands for X and Y respectively. When you're talking about now going back to the coordinates. Again, all this was from 2 work. Now, the ratio theorem, when we want to talk about the ratio theorem, we noted that when we were looking for the midpoint, we took 1 out of 2 of A, then 1 out of 2 of B. 1 out of 2 of A, then 1 out of 2 of B. It was so because the ratio here was 1:1. It was so because the ratio was 1:1. So when we were looking for the midpoint, that was designated capital M. So we took this 1 out of the sum of these 2 of A. Then the other 1 out of the sum of the 2 of B. Generally, we would say that the position vector OT, if we were to use our diagram here, we normally take that ratio, the one that I've circled, ratio N. We make it to be the numerator, like we took 1 out of 2. So we take that N, make it to be the numerator, over total ratios, that is M plus N, like we said 1 out of 2. So it was 1 over 1 plus 1. So total ratio will be M plus N into the first vector, that is a vector A. Then we add, remember we said plus a half B. We said a half B. So in the second one, we take the second ratio. which is M, we say M over, again, remember we said 1/2. It was 1/1 plus 1. But now that we are using general case, we say M plus N into the second vector B. So by so doing, we are going to get the position vector OT. By so doing, we get the position vector OT. So technically what we are saying is the ratio theorem states that if we have the line AB or we have the vector AB, then we have some point T dividing the line AB in the ratio MN. Like we've said in the, we are illustrating in the diagram. I've started by saying if we have a line AB, then we have some point T divide Are you hearing me?
Yes.
Yes.
Okay, in the process of just stating what the ratio theorem is before somebody called. So I was saying, if we have the line AB, then we have a point T dividing the line AB internally in the ratio M/N. You hearing me? Okay. So we've said we first started by saying that we have the line AB, that is a line AB. Then we have some point T. T is dividing AB in the ratio M/N, like we've stated there. Then the position vector of OT, the position vector of OT will be given by N over the sum M plus N into the first vector. Then we take M over M plus N into the second vector. That is technically what we call the ratio theorem. Hivyo iko sawa sasa?
Yes.
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 Okay. Now, I want us to apply it now, but everybody should try it on their own for a minute. I give you like three or so minutes. You test that theorem. Kama tumeipata hiyo theorem, just a minute, I share some question. We try and see how it is used. Okay, can you see what is on the screen?
Yes.
Somebody to read the question for us.
We can't see the question.
Okay, just a minute. I hope now the question can be seen from your end.
No.
No. No.
No.
No.
No.
Are we there now?
Yes.
Okay,
Yes.
take about 3 minutes and see what you can do with that question. Now having known what ratio theorem is, just about 3 minutes.
Yes.
You get feedback after 3 minutes. We should be finishing now. I see somebody has sent the responses for part 1. That is part A, 1 and 2. Five, -4, 5. That is correct. We have a third q plus 2/3 of p. That is correct for Roman 1. Then we have as a 5i minus 4j plus 5k. That is very correct. So I see at least we are now moving somewhere. Anybody with a concern before we can look at it together very fast? Any concern? Anybody who is lost? Okay, maybe we can look at it very fast. There is a solution there provided. I hope we are all able to see it. Can we see the solution on the screen?
Yes.
Okay, now remember, we are using the ratio theorem because we are doing division of a vector. Whenever you see division of a vector, some vector that has been divided into some ratios, always remember the ratio theorem. And we started by describing what ratio theorem is. So in the solution there, they are saying what the ratio theorem states. We are required to express R in terms of P and Q. So, and remember R, that is the small r, is the position vector OR. We get OR by taking n over the sum of the ratios multiplied by the first vector, that is P, then M, the second ratio, or rather the first ratio over the sum of the ratio times the second vector. And in this case, the ratio was 1:2. So that tells you that M is 1 and N is 2. Concluding that R will be given as 2 over 1/3 plus 1 over 1/3 of Q, 2 over 1/3 of P and 1 over 1/3 of Q. Now that was the first part, expressing R in terms of P and Q. Now in the second bit, now this is where we now multiply, or rather we get now the actual vector. We have P provided, we have Q provided, and we know that R is 2/3 of P plus 1/3 of. So in the question, we had P, Q as coordinates. If they are coordinates, it means what? We can create their position vectors so that we have the vector P. And having the position vector, we make it to be a column vector. From the position vector, which were provided for by the coordinates, what we've mentioned right from the beginning, we just create a column so that the 6, the -3, the 9 from P will be representing X, Y, and Z. This is 3-dimension. The 3, the -6, and the -3 in Q coordinate will be written as 3, -6, -3 to represent the X, Y, Z in the 3 column. Then after that, we take R to be 2/3 of P and 1/3 of, so that finally we get R to be 5i minus 4j plus 5k after we've multiplied the two scalars, that is 2/3 and 1/3 with P and Q respectively. Then after getting that, we get OR as 5a minus 4j And because it's a position vector, we take the 5, the 4, the -4 and the 5 to be the position X, Y, and Z. That is okay?
Yes.
Yeah.
Yes.
Okay. Vector that been, sometimes you can get a vector that has been divided. We use the same principle. But now here you have to be careful because we've been told that the division is external. Either they will tell you that the division is external, or they'll give you MN in a way that will suggest that it is external. For example, if you're given that some vector has been divided externally in the ratio, let's say 4:2, umeambiwa externally, alafu ukapewa ratio ni 4:2. Your M is to N will be what? The M will be 4, while N will be -2. Why are we saying -2? Because if, for example, I was to draw that, so we have 4, we have, let's say, A, then 1, 2, 3, 4, like that. A to B, four units, then to T, 2 units. So T divides AB externally. It is outside the length AB. So it has divided it externally in the ratio 4:2, because A is to B ni 4. T is to B ni 2. So we say 4:2, but externally. You can as well say from A to B, 4. Then B to T, 2 units, but on the opposite direction. Remember, division itakuwa A is to B, then B is to T. We normally take the first point to the division point, then division point to the other point, like that. Or not like that. This was external, so it should have been A to T, then T is to B, like that. A is to T. We take the point we are starting to the point that divides, then the point that divides to the other point. So A is to T. A is to T, then T is to B. If that is the case, then I think this diagram is not very accurate. Let me redo the diagram. We've been told that A is to T, 4:2. So let's try and illustrate that in a small diagram. And we've said what? That division unachukuaga the first point to the dividing point is to the dividing point to point 2. Hivyo iko sawa so far?
Yes.
So tuchukue from A to T ni 4 units. A to T ni 4 units. So A, 1, 2, 3, 4, T. Alafu T to B, 2 units, na tumeambiwa ni external. Tunaenda the opposite direction. 1, 2. So B itakuwa somewhere hapo. Sijui kama tuko sawa?
Yes.
Yes, we are.
Kama ni external,
Yes,
or
we
rather,
are.
in all the division, tunachukua the first point, we count the number of steps up to the point that intersects, or rather divides. Then we take the point that divides to the next point. So A to T, tuna count 4 units. Then T to B, tuna count 2 units. Lakini tumeambiwa ni external, so tuna take the opposite direction. So having said that, I was saying there are two ways that you can be given this. Unaweza ambiwa the division is external, alafu upewe the ratio ikiwa like that, 4:2. Ama pia unaweza ambiwa T divides AB, lakini sasa uambiwe with the ratio 4:2. They omit the word externally. So if they omit the word externally, yet they imply external division, the second ratio should be negative. So the moment you see that the second ratio is negative, know that the point is dividing externally. Alternatively, they can use the word externally, but give the ratios like we had initially given, 4:2. They tell you it is an external division. Wakupea ratio. Are you on mute? If you're on mute and you are responding to a question. I hope nasikizana. Okay, now I want you to do the question again. The question that we had started with P given and Q given. Alafu we divide externally in the ratio 1:2. The same question that we are working with, where we are given P ni 6, -3, 9. Alafu Q ni 3, -6, -3. Na sasa nataka sasa we divide in the ratio 1:2, but externally. 1:2, but now we do it externally. That one is to take you 2 minutes, because now at least we know what ratio theorem is and we know how to use it. So at least 2 minutes, the same vector, but you divide it externally, ratio 1:2. I hope that is clear.
No.
I am saying we had a vector that we had worked with. Let me share it in a minute. There is that question on the screen. The same question we had worked with, okay?
Yes.
Are we together?
Yes.
Now we get another question. We say a point R divides PQ externally in the ratio 1:2. So the only point we've altered is the second sentence that starts a point R. So alter it so that it reads, a point R divides the line PQ externally in the ratio 1:2. So 2 minutes. I hope now the question is clear.
Yes.
Okay. You share your solutions in the messages part so that I see once you're done. Write your solutions in the messages part. Okay, I can see we have various solutions. Maybe we can look at it together and see which one is maybe more correct. But a majority of us are giving solutions that are almost close together. So maybe the errors came from some addition or some subtraction of vectors, some multiplication of vectors with the scalars. But the progress is good. We are on the right track. So you have to be very cautious when you're doing your multiplication of vectors, especially with scalars, in situation where mostly we are using negatives. Okay, now let's see whether we can do it together very fast. I hope you can see the screen.
Yeah.
Okay, we have we have 6, -3, and 9. 6, -3, and 9. Then we have 3, -6, and -3. Tumeambiwa the division is external. The ratio is 1:2. So again, look at the wordings. External, the ratio 1:2. So it implies that M and N, ukitafuta sasa M and N, to bring out the aspect of external division, M:N will be 1:2. So that we bring out that word external. When you're writing that word external, when writing the ratio, the second one becomes negative because of what we illustrated in the diagram we started with. So they can tell you the division is 1:2, or they can tell you the division is external 1:2. Now, having said that, we go back to our ratio theorem. Our ratio theorem states that we take the first, we take n, and in this case, n will be -2. So we'll take -2. Huyo mwenye nasikia kule nyamazika. We need audio to come from one end, so check your audio. Check your audio is muted. Okay, now we take n in this case being -2, because that is our second ratio. Then the denominator, we take the sum of m and n. So we'll take 1 plus -2, so that we have -1. Then in bracket, we put the first vector as now a column vector, which will be 6, -3, then 9. We close that. Then we say plus. The second one, we will take the first ratio. The first ratio is m, and m in this case is 1. So we take 1 over the sum of m and n. So that is 1 plus -2 to give you -1. So -1. Then we put the second vector. Q was 3, -6, -3. So that one expressed as a column vector, it will be 3, -6, then -3, like that. So far so good. Kila mtu ako na sisi?
Yeah.
Now from there the
Excuse me, sir.
yes.
Can you illustrate it diagrammatically, please?
Diagrammatically, maybe we could have something like this. We had the first one P here, then we had Q there, then we are talking of an external division R there. Like that. This is P, this is Q, then this is R. So R divides Mn in the ratio 1 is to -2. So I have seen now why you're asking that question, because theoretically this one is doable, but ukichora kwa diagram it will not come out. Or maybe
Yes.
we take 1 unit. If we were to take 1 unit, then -2, it will be on the other side of P. I get now where you are. Mathematically this one is not very correct, sindio?
Yes.
Kwa sababu -2 itapita. But let's do it theoretically, assuming we just wanted to see the application of the theorem. Maybe the ratios we've taken and the equation are not appropriate, but for the purposes of illustration, let it just flow, okay?
Yes.
Maybe you can have a different question for external division. Nimeona where your concern is. Ukichora inatoka differently, because 1, then -2, it will go the other side that is greater than 1. Okay.
Yes.
But for the purposes of illustration, let it just flow. Okay.
Yes.
Okay. Now we were saying we take the first, the second, which is n over the sum, then m over n, m over m plus n. So far tuko sawa, ndio? The working is okay so far.
Yes.
Now from here, I believe the different versions of the question of the answers were coming because of the way you multiplied your scalar with your vector. Scalar by vector, scalar by vector. The first scalar is +2. So you should have that in mind, that the first scalar is +2. Then the second scalar is -1. The scalar is just the number that is before the vector. Remember multiplication of scalars by vector. You multiply each scalar by each element in the vector. So scalar ya kwanza ni 2. 2 by 6 inakupea 12, sindio? You get 12?
Yeah.
So we have 12. Then 2 by -3, we get -6.
Yeah.
Just a minute. Then 2 by 9, we get 18. So that is the first scalar multiplied by the first vector. We've gotten 18, like that. So we add these two. The second scalar was 1 divided by -1, which will give us -1. So -1, we add multiplied by 3, unapata -3. Then we have -1 multiplied by -6, unapata 6. Then -1 multiplied by -3, we get +3. So far, so good in our multiplication.
Yeah.
Yes. Yes.
Then from is addition of vectors. Addition of vectors, remember we add vectors in corresponding position. We add x to x. So 12 plus -3 to give you 9, right? Then we have -6 plus +6, we get 0. I believe that's where now the concern we are having is being manifested. 18 plus 3, we get 21. Hivyo iko sawa?
Yeah.
So that will be the column vector for position R. Column vector for position R. So OR will be 9I 0J, or we can skip the J. We say 21, 21K. So it has been reduced to a two-dimension vector. I believe that is the error that we created from the question we were in. But nevertheless, that is what we are supposed to have. If that error was persistent, we should have the persistency given answer. So see, I believe now it has flowed, right? Right?
Yes.
It has moved. What we wanted to achieve has been achieved. We have now illustrated how to use external division of a line using the ratio theorem. That was the point. How do you divide a line externally using ratio theorem? Maybe I will share a better question that will not have these issues, but at least we've seen what you're supposed to do. Sammy Nelson, your hand is up.
Would it be wrong to include the J part of that equation as much as it's 0?
There is nothing wrong. We can say plus 0J. We can say 9I plus 0J plus 21K. That is still correct. Okay. So point is, if we have external division, make it M:n, but take the n to be negative. The negative n is what brings out the aspect of external division. So the question will tell you a certain ratio, then you're told it is external division. So it is upon you now to make that n is negative. If the question has not said external division, but it has given you mn with n being negative, it implies that the division is external. Hivyo iko sawa?
Yes.
Okay. Now, I believe that is all for ratio theorem. You need to look for very many questions so that you can practice it and internalize it. Maybe for the remaining part of the time, I want you to look at the question 29 on the screen. Can you see question 29?
No.
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 Yes.
No. Nope.
No.
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 It is now on the screen. I hope.
Yeah, yeah.
Yes, yes.
Okay, now that is a different concept. We are done with the ratio theorem. I've said make sure you do a lot of practice with the ratio theorem so that you get it. Abdul Malik, your hand is up.
Yes.
Yes.
Is there by any means that we can use ratio theorem when the originating point is not necessarily 0, 0 in the Cartesian plane?
In most cases, we talk of position vectors. When we are dealing with the ratio theorem, we talk of position vectors. And position vectors are called so because they originate from the origin of the Cartesian plane. So the ratio theorem works perfectly with vectors that come from the origin. We work with position vectors. Position vectors, vectors that are going to give us coordinates, because we are looking for coordinates of some vector. And for you to get coordinate of a vector, or rather, for you to get a coordinate of a point using vectors, we need to relate it to the origin of the Cartesian plane. I hope that is clear.
Yes.
So we normally work with IJ, IJK, IJ for 2 dimension, IJK for 3 dimension, and we are talking of coordinates in relation to position to their position with respect to the origin. So they work perfect with vectors that originate from the origin of the Cartesian plane. So in a minute or two, attempt question 29. It's a different concept altogether, but nevertheless, just go through it in 3 or so minutes so that we see how far we are in testing, or rather in understanding collinearity. 2 or 3 minutes.
ziko hapo. Tuangalie kama zote zimekuwa marked.
Zima mic. Boys may carry out quick roll call. Quick roll call. Let's get it roll call. Look at the screen. Look at the screen.
Where chocolates was in a
Quick roll call. Look at the screen.
How is the progress?
Still doing.
We're doing a roll call.
Okay.
We're doing a quick roll call. Mr. Mburu.
Yes, sir.
Mr. Mburu, you can hear me?
Yeah, I can hear you.
Mr. Mburu, can you hear me? So boys,
Loud
just
and
read very
clear.
quickly. Can you see 139 I've done? Mr. Mburu, you can hear me?
Yeah, I can hear you.
Mr. Mburu, can you hear me? So boys, just read very quickly. Can you see 139 I've done? We are at 161 now out of 197, and that's less than 80%. We still have some boys who have not answered the roll call. 166. Yeah, 171. It's 86%. I want at least 90% of the participants. 171 of 198. You can see 172. It is taking some students too long to respond. Something that should take you less than 3 seconds to finish. Pick your class, submit. And for those who don't get this roll call, you update your Zoom app. If you're using your phone or your computer, just update it. There's a newest version on Play Store and also online for that. We're at 9%. 89%. I wanted to stop it at exactly 90. Or at least 90% of attendance to know. So A with 27 students, I can see Q has only 11 who have responded. So A and R have 27 students, which is good. Okay, good. Now I see A has gone to 28 and R still remaining the same. Okay, we're at 91 and therefore I'm starting the roll call now. Thank you. So A and R have 27 students. Good. I see A has 28 and R is remaining the same. Okay, we're at 91 and therefore I'm starting the roll call now. Thank you. And
How far with the question? How far are we? I remember these are short questions, so we may not expect some answers the way we normally give the conventional way of giving answers. Instead, we demonstrate. We give a proof of collinearity. So I hope you are somewhere.
Yes.
Okay.
Yes.
Now let's do it together very fast. These are another part that is commonly tested, especially in section 1, proving of collinearity. Collinear basically means they are sharing a line. You have some positions there. We are told position vector of P, Q, and R. Then you're given the position vectors as column vectors. So that should not trouble you by now. We've interacted with vectors enough. P is a point, Q is a point, R is a point, and that's why they are not in bold. Those are coordinates. However, they've been written as X, Y, Z as a column vector to show that these are positions with respect to the origin of the Cartesian plane. You're given them there, the three of them, as column vectors. Then you are told to show that P, Q, and R are points that share a line. P, Q, and R are points that share a line, or in other words, you test or show their collinearity. Now, for testing of collinearity, we have two things that we have to prove. Number one, we have to prove that some two vectors that we are going to create are parallel. So we look for parallel vectors. Then number two, we have to show that there is a shared point among the set of the two parallel vectors. So you have a common point or a shared point, common point. So those are the two things that we use to prove collinearity or to show collinearity. Number one, parallel vectors. Number two, common point. Those two parts must be there. Both of them should be there for you to prove collinearity. If we have a common point and no parallel vectors, they are not collinear. If we have a common point and no parallel vectors, maybe something like that. If we had P, Q, and R, I hope all of us can see my left part of the screen. What I've written P, Q, and R.
Yes. Yes.
So we have a common point Q. However, if you are to calculate this, you'll see that PQ is not parallel to QR. So we are missing one bit. That is the parallelness, or the one vector being parallel to the other. And therefore, in the left part of the screen, those are not collinear. They are not in a straight line. They are not sharing a line, although they have a common point. Then we can have some vectors that are parallel, but they don't share a point. We could say AB, PQ, then we put those arrows there to indicate that they are parallel. PQ and OB, they are parallel, but they are not sharing a point. So they are not collinear. So the aspect of sharing a point is not there. Now, for you to have collinearity, the two must be there. One, we have to have some vectors that are parallel, yet they share a point. PQ may be parallel to QR, but they are sharing Q. So if you are able to prove the two, that is parallel, then number two, a common point, the combination of those two will lead you to conclude that the points PQR are collinear. Now the first bit, how do you prove that a vector is parallel to the other? How do you prove a vector is parallel to the other? Now for it to be parallel to the other, it has to be a scalar multiple of the other. That is to say, we take a scalar, multiply by some vector, you get the second vector. A scalar, multiply by the first vector, you are going to get the second vector. That's what we are calling a scalar multiple of the other. If that is the case, then they are parallel. If that is the case, then they are parallel. An example may be, if we work with a Cartesian plane, in Form 2, we had what we are calling equivalent vectors. So that if we have vector A here and vector A here, we say they are equivalent, provided they are facing the same direction like that. The scalar in this case is 1. These multiplied, the first one multiplied by 1, you get the other because they are equal in distance and equal in, they are facing the same direction and equal in distance. If we make this one above here to be 3A, the other one to be A, they don't stop being parallel, they are parallel. However, they are not equivalent, but one is a scalar multiple of the other. You take the first one, you multiply by 3, you get the second. The scalar here is 3. So the first vector A multiplied by the scalar 3, you are going to get exactly the second vector. So if you show that the first vector multiplied by some scalar will give you the second vector, then you've proved or you've shown that they are parallel. Hivyo iko sawa?
Yes.
Now let's take the vectors. We will create vectors from these position vectors. We have the position vector P, we have the position vector Q, we have the position vector R. So the first vector we can create is maybe PQ. We create the vector PQ, then we create the vector QR. Vector PQ, then QR. We start by checking whether they are maybe scalar multiple of the other. If they are scalar multiple of the other, we conclude that they are parallel. So what is vector PQ? We were given P as 1, -1, 3. Now for you to get PQ, remember we say Q minus P. This is a concept we did in Form 2. I hope all of us can remember how we got Q minus P to be QP.
Yes.
In form.
Yes.
Yeah, because of the issue of direction, because of the issue, we want to move from P to Q, but we want to move along vectors that have been designated small q and small p. Eventually, we would have done Q minus P. That is something we did in form 2. So we take Q. Q is 3, 3, 1. 3, 3, 1. I hope my screen is visible.
Yes.
Then we P. P is 1, negative 3, 3. 1, negative 3, 3. You get the difference, you're going to get the vector PQ. So what is PQ? You get to 6,
44.
264, right? Is it 264?
No.
Oh, it was
1, negative 1, 3.
negative 1. 1, negative 1, 3. So it is 2, 4.
4,
2 for negative.
negative
2.
Yeah.
2 for
2
negative.
for negative 2.
2,
2
4,
for
negative 2.
negative 2.
Yes.
So I had written my P wrong. So 1, negative 3, 3. So let's correct that. It is P 1, negative 1, then 3. So 3 minus 1 to give you 2. Then we have 3 minus negative 1 to give you 4. Is that correct?
Yes, sir.
Then
Yes.
1 minus 3 to give you negative. Okay.
Yes.
So PQ becomes what?
2,
2, 4, negative 2.
negative 2.
2, 4, negative 2. Then we look for the other vector, that is QR. We look for vector QR. The same procedure, we take Q, we take R minus Q. R minus Q. R is 6, 9, negative 2. We minus 3, 3, 1. We end up with what?
3, 6, negative 3.
3, 6, negative 3.
6, negative 3.
3, 6, negative 3.
Yes.
Yes.
That is QR, right?
Yes.
Yes.
Now, how do you check whether one is a scalar multiple of the other? How do you check whether one is a scalar multiple of the other? You can take each element, divide by the corresponding element, and see whether there is some consistency. For example, in QR, the one taking X, position X is 3. The one taking position Y is 6. The one taking position Z is negative 3. In the other one, PQ, the one taking position X is 2. The one taking position Y is 4. The other one taking position Z is negative 2. So let's see, 3 divided by 2. Unapata nini? 3 over 2, right?
Yes.
1 point. Yes.
Aya, ukichukua 6 divided by 4, we are dividing elements occupying the same positions. Y hapa ni 6, Y hapa ni 4. 6 over 4 inakupea 3 over 2, sindio?
3 over 2.
Finally, negative 3 divided by negative 2.
3 over
3
2.
over 2.
3 over 2.
So we can see that there is a common scalar, or rather there is a common quotient if you are to divide all the corresponding elements. So we will therefore see that ukichukua ya kwanza PQ multiply na 3 over 2. 3 over 2 into PQ. 3, 4, negative 2. Utapata ya pili. Ya pili ni 3, 6, negative 3. Okay? Iko hivyo?
Yes.
Yeah. Now we can say that if you take the first vector, multiply it by a scalar. Scalar is 3/2, you will get the second vector. So that means the first vector is a scalar multiple of the second vector. The first vector is a scalar multiple of the second vector. And remember, we said that if you have such, it means that the two are parallel. So if that is the case, we said that 3/2, the first vector, you write that 3/2, the first vector. What was our first vector? Was it PQ?
Yeah.
Yes.
3/2 PQ equals QR. And remember, these are vectors, so you put a direction there. 3/2 PQ equals QR. This is just to say, in other words, PQ is a scalar multiple of QR. And if that is the case, we say that PQ is parallel to QR. If you've shown that PQ was a scalar multiple of the other one, you conclude that PQ is parallel to QR by the fact that the first one is a scalar multiple of the second. Now that was the first bit to show that the two vectors are parallel. That was the first bit to show that the second vector, or rather the two vectors are parallel. Now to finally conclude or to show collinearity, you have to have one shared point. Now in this case, what is the shared point?
Q.
Q.
So you say that
Q.
You finally state, you have to show that Q is a common point. Q is a common point. Therefore, P, comma, Q, comma, R are collinear. Iko sawa?
Yes.
So tunasema vitu mbili. Ya kwanza ni kushow that they are parallel. And how do you show parallelness of vector? Show that one is a scalar multiple of the other. That one is a scalar multiple of the other. Then number two, show that we have a common point. So that now if you put the parallelness plus the common point, the conclusion is therefore PQR. And remember, the PQR here are coordinates, so don't write them as vectors. These are points. P, Q, and R are collinear. So kwenye unaandika kama vectors, ni hapa kwenye tulikuwa tunasema mambo ya parallel. Hizi ni vectors. So usisahau kuweka the line above. Lakini hapa P, Q, na R, these are points that you were initially told to show that they are collinear. Our time is up. I will share with you, I don't know how, but I will look for some questions on the first concept we discussed, that is the ratio theorem, then some additional question on collinearity, so that you go through them. And there is another bit where you are supposed to look for some fractions. Maybe you are told that this vector is like this, then OX is H, those type of questions. I'll look for some, then share maybe through your through them. Make sure you practice and practice. These are almost sure bet questions. They will be there in your KCSE. Okay.
Yes.
So make sure make sure you're very conversant with collinearity, ratio theorem, looking for some fractions. Here, kutafuta fractions, I will look for some questions, then we can go through them. Thank you for your availability today. See you Friday, God willing.
Thank you.
Thank you.
Thank you. Thank you, Alliance.
Thank you.
Mr. Mburu. Mr. Mburu.
Yes.
Mr. Mburu?
Yeah, somebody is calling.
Mr. Mburu?
Yes, I can hear you.
Yeah, there's another session on Friday.
Yes, there's a session on Friday.
Okay.
Yeah. Friday afternoon, I believe so. And the last session for the day, Friday.
Thank you.
Yes. Okay.